Okay, hello everyone, good morning. We're officially recording now. So today we start the second week of the course. And just before we start, I want to give a reminder that everyone that is interested in registering for the reading group should send an email to Cheyenne before tomorrow's lecture, so that we can have an idea of who is interested in participating, and then further details will be communicated afterwards. Okay, so Nicole, thank you again for being here, and the stage is yours. Thank you. I think you're still muted, Nicole, sorry.
Thanks for letting me know. Great, thanks for the setup. Today, we're going to quickly review what we talked about in the last lecture, then move on to thermodynamic resource theories, which I will often abbreviate as TRTs. First, we'll talk about the different classes of TRTs, from most specific to most general. Then we'll talk about the elements that define a TRT. We'll talk about a couple of results. First, necessary and sufficient conditions for one state to be able to transform into another for free under free operations. And then we'll talk about monotones, which are sort of like the free energy, but there are a lot more of them. I have a couple of announcements. First, if you wouldn't mind, it would be wonderful to see photos or screenshots of you guys participating in the course. If you wouldn't mind posting them on social media in the future so that we can tell a story about the course. So if you wouldn't mind doing that, please feel free to send your photos and screenshots to Gabriel at his email address here. And also, there were a couple of homework problems provided in the last lecture. I'll post the solution to those online today. Here's a quick review of last lecture. We have been proceeding across the landscape of quantum thermodynamics, moving around this map of quantum thermodynamics that's full of different city-states, different sub-communities that have different toolkits and different perspectives on quantum thermodynamics. On Friday, we talked about fluctuation relations, and we started talking about resource theories. The fluctuation relations, we said, are equalities that strengthen the second law of thermodynamics and govern systems even far from equilibrium. We saw the example of a strand of DNA floating in some aqueous solution at an inverse temperature beta. We can use optical tweezers to trap one end of the DNA and pull the other end. This pulling costs work. The work changes from trial to trial. So you can build up a probability distribution, P of W, over the possible values of the work. That probability distribution obeys Jarzynski's equality, which implies this implication of the second law of thermodynamics. We also derived Crookes' theorem from a forward process and a reverse process. We also looked at some quantum fluctuation relations, looking first at the two-point measurement scheme for distinguishing work from heat. We derived the Tasaki-Jarzynski equality, and a lot more has been done on quantum fluctuation relations. Then we got an introduction to general resource theories, which consist of, in most cases, three key components: free systems or states, free operations, and resources, which are not free. Today, we're going to move on to narrowing our focus to thermodynamic resource theories. Can suggest a couple of references. A number have been written now. One is the review about thermodynamic resource theories generally that I suggested at the end of the last lecture. There is a section about thermodynamic resource theories, and you can see how these resource theories fit into the broader resource theory framework. Also, Matteo has written some lecture notes. There are multiple classes of thermodynamic resource theories. There's a sort of tiered hierarchy, because thermodynamics describes lots and lots of different situations. Steam engines, electrochemical batteries, a mug in which you have coffee mixing together with cream. One thermodynamic resource theory models a few thermodynamic situations. Then a larger class of thermodynamic resource theories models a larger set of thermodynamic situations. And the most general class models all thermodynamic situations. So I'm going to start with the simplest class and then generalize. The first is called the resource theory of non-uniformity, which is a funny name, but we'll see why it has that name. It models closed isolated systems. In other words, thermodynamics at a fixed energy and particle number and other extensive quantities. You could also say that this resource theory models information processing. I personally like to think of information processing as just thermodynamics at zero energy, say. There are two versions of this resource theory. We can model discrete quantum systems and discrete classical systems. This resource theory was first laid out by several Hordetskis and co-authors. In 2003. Then co-authors and I wrote a very long, thorough review with old results as well as a bunch of new results, including a single shot analysis of single copies of a system. What are the objects of interest in this resource theory whose transformations we track? In the quantum version of the theory, these are density operators, rho. In the classical version of the theory, they are probability distributions. Which have, for instance, d elements. Such a distribution could model the outcome of the roll of a die or the outcome of a measurement of a quantum state, say relative to its eigenbasis. Either event can be represented by some random variable x, which assumes possible values x1, x2, and so on up to xd, wherein x has a probability p sub j of equaling x sub j. In most problems, the quantum version of the resource theory reduces to the classical version. At least in most problems we will be, or all the problems we will be interested in. We'll see one reason why in a few minutes. A full discussion is in the Gur et al. Paper. So you can use quantum states if you want to, but the only properties that matter are their spectra, which are probability distributions. So sometimes I'll use quantum notation because it's simple and it's familiar to quantum information theorists, but everything that we'll discuss in the resource theory of non-uniformity can be expressed in terms of probability distributions. What are the free states in this resource theory? Well, we're modeling, as we said, information processing. If you value information, noise is all too easily accessible. How should we model noise? Well, how should we model information? Information can be defined as the ability to distinguish possibilities or alternatives. In other words, to predict outcomes, such as the value of our random variable x. We can predict the value of x if one of the x sub j's is more likely than the other x sub k's. So if one probability p sub j is greater than other probabilities, which means that the distribution is uneven, it's not uniform. So a uniform distribution encodes a complete lack of any information, which we can think of as noise. So the free states are uniform states or distributions. In the quantum resource theory, these manifest as density operators of the form the identity over the dimensionality of the state space, the maximally mixed state. In the classical version of the resource theory, the uniform distributions have the form 1 over d, 1 over d, and so on. The free operations along these lines are called noisy operations. We start off, if I can write, there we go. We start off with some initial state rho, and then take 3 steps. So each free operation consists of 3 steps. First, we can add noise to the system. We can tensor on a uniform state. Then we can perform any unitary on the joint system. This will scramble up the information with the noise. Then we can discard any subsystem. Which I'll call A. Now we can see better why the quantum resource theory reduces to the classical one. Suppose that we have some quantum state rho that, relative to our favorite useful eigenbasis, or excuse me, basis, is represented by a matrix that has off-diagonal elements. So this looks like a problem that has the potential for quantumness in it. Well, we can just apply the appropriate unitary for free so that that rho becomes diagonal. So the rho is equivalent via free operations to just a probability distribution, because a diagonal matrix consists essentially just of a probability distribution and some zeros. Now we've talked about free states and free operations. We should now mention the resources. These are all non-uniform states or distributions. Hence the funny name for the resource theory of non-uniformity. This resource theory can be useful even when you are really interested in more general thermodynamic resource theories. Suppose that you're working in more complicated resource theory and you need a simple limit so you can understand the basics of what's happening. Then set all of the extensive observables to be totally degenerate, maybe equal to 0. Then you can work in the resource theory of non-uniformity. All you have to worry about is information. You don't have to worry about keeping track of energy or particles, and you can gain often insights into the problem. Let's now take a minute-long break, rest our eyes from staring at the computer screen, and visualize what we just saw and heard. Are there any questions about the resource theory of non-uniformity? At the beginning, you said this was built for discrete systems. Why can we not use it in continuous variable systems? The resource theory is defined in this way in part because of physical motivations. A lot of quantum information theorists like working with qubits, and so that was the motivation for defining the resource theory this way. We can generalize some of the results to continuous settings. We just need to do that explicitly. In some cases, there could be a problem with identifying a uniform measure on the appropriate space.
There's also a question from YouTube.
Okay.
So Junan Ling asks, why are unitaries considered as free operations?
The unitaries, loosely speaking, you can think of as scrambling up the information. So there's probably some useful information in this initial system of interest. And then here's noise. The unitary will tend to mix up the information and the noise, so it's sort of difficult to recover. And you could expect intuitively that if information is valuable, then it all too easily does get dispersed and mixed up with noise. Is the fact that these operations can always be mapped into distributions due to the free states being diagonal in any basis. Is it the same if your free states are generic thermal states? So So we actually are just about to move on to resource theory in which the free states are Gibbs states, Gibbs thermal states. So we'll talk about that in just a moment. You say you can diagonalize for free. Is this true for any basis of this subsystem? Yes, because you can apply any unitary you want for free. The next tier in the set of thermodynamic resource theories consists of the resource theory of athermality, which also is a somewhat funny sounding name, but that just means resource theory for resources which are away from thermal equilibrium. So this is the resource theory used most often in the literature. It models exchanges of energy or an agent in a fixed temperature environment. This temperature we will call T. The inverse temperature is beta, where K sub B is Boltzmann's constant. Some of the earliest references about this resource theory came out quite a few years ago. Although in 1998, when this resource theory, or excuse me, when this paper came out, the resource theory framework had not been formalized. The first formalization of this resource theory under the resource theory framework banner occurred in this paper. And much more has been written. How do we model a system of interest? We associate each physical system with a Hilbert space, which I'll denote by curly H. Defined on that Hilbert space are a density operator and a Hamiltonian. The free systems are those at thermal equilibrium relative to the environment's temperature. Because we imagine that the agent can just draw off one from the bath. In fact, in our very simple model, we imagine that an agent in this environment can just dream up his or her favorite Hamiltonian, H sub B, and pluck a system at thermal equilibrium relative to that Hamiltonian and the fixed temperature from the bath. So we suppose that every single state of this form is free. That is not the most realistic assumption because a real experimentalist can't create systems governed by arbitrary Hamiltonians, but this is a simple model for mathematics' sake. Multiple sets of free operations have been defined. I'm going to focus on one of the simple early sets. These are called thermal operations. Many variations on these have been defined. An operation begins with some system of interest, and it transforms as follows. Again, we can perform 3 steps to perform a thermal operation. First, the agent can draw from the bath a piece of the environment that's at thermal equilibrium and bring it over to the system of interest. We have this initial states, and we can tensor on whatever thermal states we like. Second, we can perform any energy conserving unitary. The unitary transforms the state like this. We demand that the unitary conserve the total Hamiltonian, by which I mean the Hamiltonian of the system plus the Hamiltonian of the bath. We're used from condensed matter and atomic molecular and optical physics to including in the total Hamiltonian plus H sub interaction, but it's the H sub interaction that's generating the U. So you can think of us as working in the interaction picture. And this is the manifestation in the resource theory of the first law of thermodynamics. Finally, we can discard any subsystem, which I will again call A, that's not coupled to the rest of the system through the total Hamiltonian. So the state transforms like this, and the Hamiltonian transforms like this. In this resource theory, the resources are athermal or not at thermal equilibrium relative to the ambient temperature. For example, as we said in an earlier lecture, if you have a fixed temperature environment and suddenly you're given a cold system, you can run a heat engine. You can let heat flow from one to the other and turn the heat into work. Work is valuable, so it makes sense to think of that cold resource not at thermal equilibrium relative to the ambient temperature as a resource. Are there any questions about the resource theory of athermality? Is the master equation a thermal operation? I recommend talking about that with Matteo. He's going to talk about master equations and resource theories. Could Hamiltonians be time dependent in this approach? That's a very good question. We can incorporate time independent Hamiltonians into our formalism by using what can be called a clock or a switch. So you have another system that can have different states, like have it effectively a clock hand that points to 1 or 2 or 3. And when the system points to, say, 1, Hamiltonian H sub 1 evolves the system of interest. When the state is at 2, the Hamiltonian H sub 2 points to this, or evolves the system of interest. So we have our, let's see, suppose that we want for our system of interest to evolve under H sub 1 at certain times, then the total Hamiltonian will be proportional to this. So the clock hand points to 1. So H2 evolves the system of interest when the clock hand points to 2, and so on. So the Hamiltonian is just, we have the Hamiltonian of the system of interest. We bring over a piece of the bath. So now the total Hamiltonian is the Hamiltonian of the sum of the two Hamiltonians. And then we can throw away a subsystem if it's not, say, part of one of these systems and connected to that the rest of the system via some coupling within the Hamiltonian. We assume a question is, could you repeat the interaction / one law part? I think the reference is to this step. We regard as free just the Hamiltonians that obey the first law of thermodynamics. The first law is conservation of energy. So we demand that the unitary that evolves the system conserves the global energy. Okay, let's move on to the most general class of thermodynamic resource theories. If I can write. Let me try to fix this. There we go. This class of resource theories consists of resource theories of non-equilibrium. These model all thermodynamic interactions, exchanges of heat, particles, electric charge, particles of different species, and so on and so forth. Or we could say that these resource theories model an agent's an environment at a fixed temperature and set of all the other intensive parameters conjugate to the extensive variables exchanged, like chemical potential if particles are exchanged. These were developed in 2016. Fuller generalization is in here. And you can ask about an especially quantum version of this problem. We represent the things exchanged, energy and particles and electric charge and so on, by Hermitian operators. So what if those don't commute with each other? This problem was simultaneously approached by 3 groups. Fortunately, we all basically agreed, which is, well, one could regard that as not terribly exciting in science or as great and reassuring. We model our system of interest or any system, any thermodynamic resource, or any thermodynamic system in this resource theory with, again, a Hilbert space H, as well as a density operator and a Hamiltonian, and more observables. These represent the other things exchanged by the system. For example, one of these could be the particle number of an operator for a particular particle species. The free systems are at equilibrium relative to the environment. This is not only thermal equilibrium, but also chemical equilibrium, electrochemical equilibrium, and what have you. So the state has this form. We have our inverse temperature, our favorite Hamiltonian, whatever the agent wants. This sum is over the exchanged quantities. This mu sub k is the effective chemical potential intensive parameter conjugate to the kth conserved quantity. We have a partition function, and then we have our observables. The free operations are called equilibrating operations. And they generalize the other free operations we have just seen. So we start off with some system, rho, h, whatever other conserved quantities we have. Then the states can have brought over to it whatever equilibrium system we please. I should have had subscript B here. We take off a piece of the bath. Now we can evolve with any unitary that conserves not only the total energy, but also the total amounts of each other quantity that's conserved and exchanged by system and bath. So that, for example, the total particle number is constant. Finally, we can discard a subsystem A not coupled to the rest of the system. The state transforms like this. The Hamiltonian transforms as before. And each of the globally conserved exchanged quantities transforms analogously. In this resource theory, the resources are, as you would expect, non-equilibrium systems. For example, an electrochemical battery contains a system that's not at electrochemical equilibrium with its surroundings, and that's why the battery is useful. Let's take another minute-long break, rest our eyes, and picture in our mind's eyes what we just heard and saw. Are there any questions about the classes of thermodynamic resource theories. Okay, let us move on to some results. We've defined these resource theories. What can we do with them? Someone raised a hand.
Okay, so
is there a framework that allows us to model an even more general situation? For example, when there are multiple baths at different temperatures. I'm thinking about heat engines, for example. Yes, if you want, you could say suppose that we're thinking about just multiple baths at different temperatures, then you could regard each of the baths as a resource relative to just one of them within, say, the resource theory of athermality. So you could say in the resource theory of athermality, there's a bath at some temperature, and there are a bunch of other baths at other temperatures. We can, according to the resource theory, these other ones are resources relative to this environment. And there have been some papers written about heat engines in the context of thermodynamic resource theories. Let's look at necessary and sufficient conditions for state transformations, from one state to be able to transform into another state for free. In the resource theory of non-uniformity that models information processing. I'm going to focus on this resource theory first because, as I said before, it's simplest. Now I'll start writing probability distributions instead of quantum states. In our setup, we have two probability distributions. I'll call them R and S. R has elements R1, R2, and so on up to R sub D. And S has elements S1, S2, and so on up to S sub D prime. I will assume that these elements are ordered loosely speaking from greatest to least. The guiding question that we want to ask is, does any noisy operation, any free operation, map the distribution R to the distribution S? Conventional thermodynamics has an analogous question. Which can motivate our question. Here we have some many particle system, maybe a gas in a box. We have in mind two equilibrium macro states. For example, in one, all the particles are clumped up together in one corner of the box. And in the other macro states, for example, the particles are all spread out across the box. In this conventional thermodynamic context, our guiding question is slightly different. We ask, can one macrostate transform into the other spontaneously? In order to answer this question, we first identify the relevant free energy, which I said I would sometimes abbreviate as Fe, or Massue function. The Massue functions are less well known than the free energies. You can approach thermodynamics in two equivalent ways. So in the energy formulation, we focus on free energies, which are Legendre transforms of the energy and which minimize an equilibrium. In the entropy formulation of thermodynamics, we focus on Massue functions, which are Legendre transforms of the entropy and which maximize at equilibrium. For example, if we have a closed isolated system, the relevant Massue function is the entropy. If we have a system that exchanges heat with a bath, the relevant free energy is the Helmholtz free energy. And if we have a system that exchanges heat and particles with a bath, the relevant free energy is the grand potential. This is the free energy or the Massue function in terms of which it's very useful and convenient to express the problem. The screen is freezing. Is the screen okay now?
Yes, for me it's looking fine, yes.
Okay, excellent, thank you. The answer to our guiding question, can one state transform into another spontaneously, is yes, if and only if the relevant free energy decreases monotonically or the relevant Massue function increases monotonically. That is, if the second law or an implication thereof is satisfied. This conventional thermodynamic problem has some limitations. We focus on the thermodynamic limits, in which the total particle number and total volume approach infinity as their ratio remains constant. And I don't have infinitely large systems. And we're also focusing on equilibrium states and macro states. So we might want to address small systems. In these infinitely large systems, self-averaging happens. We might not be interested in averages. We might be interested in small systems and single copies. That's a reason to recast the question in the resource theory. To ask, is there any free operation that maps one system to another? Well, let's go back to that question and reason about it physically. Probability distributions, or information, can grow noisy for free all too easily. We said that noise is represented by uniform distributions. So we should expect that our resource states, or one state can transform into another state for free via noisy operations if S is noisier than R. So if S is more uniform than R. So we need some mathematical toolkits that gives us a measure of closeness to uniformity. That toolkit is called majorization. Again, it's a mathematical toolkit for quantifying a distribution's closeness to uniformity. In more general thermodynamic resource theories, we use a generalization of majorization that tells us how close a distribution is to the equilibrium state. An excellent reference about majorization is a book by Marshall, Olkin, and Arnold. Also, a lot of the information in that book that is relevant to physicists and thermodynamic resource theories appears in this giant paper about resource theories, phrased in physicist language. It's interesting, parts of majorization were actually developed in economics in the early 20th century because economists wanted to quantify how unevenly wealth was distributed across a population. So sometimes you'll come across in majorization theory some terms that refer to economic situations. Mathematically, majorization is a preordered. A preorder is a binary relation defined on some set S. This will be a curly S. In our case, a set of probability distributions. There are two properties that define a preorder. First, a preorder is transitive. If R lies above S in this preorder and S lies above T, then R lies above T. Second, a preorder has reflexivity. So loosely speaking, every element in the set is at least as great as itself. How shall we define this preorder? We should consider two cases. First, suppose that the dimensionality little d of our probability distribution R is the same as the size little d prime of our distribution S. Then R majorizes S, which we write in this way. If certain partial sums obey a certain inequality. So let's take the first elements of the distribution R, which you remember were ordered from greatest to least. So that wasn't supposed to happen. There we go. We take the first big J of the elements of our distribution R and we sum them. We form the same sum from the first big J elements of S. And big J can run from 1 to D. So if this inequality holds for each of these sums, for big J equal to 1, 2, D, and so on up until D, then R majorizes S. That means that R is less uniform than S. We'll see some examples that will provide some intuition. Now suppose that D doesn't equal D prime. Let D double prime be the least common multiple of D and D prime. But let's now think physically. In the context of information processing, in the resource theory of non-uniformity, tensoring on a uniform distribution is free and discarding a uniform distribution is free. So we can tensor onto R, the distribution, a uniform state of size D prime, while we tensor onto S, a uniform state of size D. So these two bigger states have the same size. So we can compare them using our part A of the definition of majorization. So saying R has the same non-uniformity properties as R tensored a uniform distribution of size D prime, and S has the same non-uniformity properties as S tensored with a uniform distribution of size D. Then we'll say that R majorizes S if the two extended distributions obey the inequalities in the first part of our definition. Let's go through some examples to gain some intuition. First, suppose that R is pure, has the form of a 1 followed by a bunch of zeros, and the two states are of the same dimensionality. Again, R has this form. Then at the very first value of big J, already when big J equals 1, this sum, this R sum, reaches its maximum possible value of 1. So the S sums have no hope of exceeding the R sums. So R majorizes S. If S is also pure, then R equals S, so S also majorizes R. Now suppose that both R and S are pure, but S is bigger, has more elements than R has. For example, R contains just 2 elements, while S contains 3 elements. I want for you to prove for homework that S majorizes R, but R does not majorize S. So I want for you to prove that mathematically. The physical reason is we can distinguish more alternatives. If given S, than if given R. If we hold S, then we can distinguish between 3 alternatives. If we hold R, we can distinguish between just 2 alternatives. So S gives us more information than R. So the length of a distribution contributes to the amount of non-uniformity of the distribution. Now suppose that R is uniform, while S is arbitrary. So R has the form of our uniform distribution, which contains just a bunch of copies of 1 over D. Then S majorizes R. How come? Well, this uniform distribution has the least possible value for its greatest element. If R1 were any smaller, then the uniform distribution would not be a probability distribution. It wouldn't be normalized. So already in our majorization condition, when big J equals 1, this RJ sum is as small as possible. So R can only be majorized by S. Does anybody have any questions about majorization? One question is, so compared to Shannon entropy, the main difference is that this takes into account the system dimension, right? We're going to see entropies later. So majorization is a more thorough measure than Shannon entropy. Actually, I'm going to talk about pretty much just this in a few minutes. Okay, let us move on to apply majorization. To the resource theory of non-uniformity. We will use a theorem that says, or you can prove a theorem that says that there exists a noisy operation, a free operation, that maps R to S if and only if R majorizes S. I'll denote the existence of such a free operation as with R, and this X maps to arrow S. The proof, I don't have enough time to provide because in order to provide the proof, I would have to introduce even more definitions, but you can find it in this 2015 paper. Well, what do we learn? First, as in conventional thermodynamics, our transformation law manifests as a set of inequalities. However, in thermodynamics, conventional thermodynamics, we can get away with just one inequality. We can check the relevant free energy, how it transforms, or the relevant mass-Sue function. But since our resource theory guiding question is more general, we have to do more mathematical legwork. We have to check more inequalities. Okay, let us take a minute-long break, rest our eyes, and visualize in our mind's eyes what we just saw and heard. Does anybody have questions about majorization in the resource theory of non-uniformity? Is this theorem equivalent to the second law? It's not. The second law consists of one inequality. Here we have a whole family of inequalities, all of those partial sums. There is an even more detailed analysis of the relationship between, not exactly this, but a generalization of this and the second law in a paper that's, well, I don't remember all of its details, but I know that it was co-written, at least in part, by Fernando Brandão, Nelly Ng, Stephanie Weiner, probably Jonathan Oppenheim was in there. But that provides a fairly detailed comparison. But also the next section can help us understand better the relationship between majorization and the second law, this one inequality. So the next question is about whether majorization is more powerful than the second law. In a way it is, and we'll talk about that in just a moment. The next section involves monotones. I'll define them in just a moment. First, let's talk about the motivation for them. In conventional thermodynamics, physically meaningful quantities, a free energy or a mass U function, change monotonically during spontaneous transformations. We can ask, does the resource theory framework predict the existence of analogous quantities? And of course, the answer is yes, otherwise I wouldn't have asked the question here. So let's define monotones. Some of which answer this question. Let's suppose that we're comparing two probability distributions with equal numbers of elements. So D equals D prime. If D doesn't equal D prime, then we can play the same trick as above, tensor a uniform state, a free state onto each distribution so that the larger distributions have the same size. Let's say that our distributions are in a state space called omega. So a function f that maps omega to the real numbers is a noisy monotone, a monotone under noisy operations, which are free in the resource theory of non-uniformity. If the existence of a free operation that maps R to S implies that F evaluated on R is at least as great as F evaluated on S. So in a loose sense, you can think of this function F as sort of like a free energy, because if R can transform into S for free, or analogously to spontaneously, then F, like the free energy, decreases monotonically. You might wonder about the converse. Does the truth of this inequality imply that R can transform into S for free? This is similar to some questions I got in the chat a few minutes ago about the relationship between the second law, which is one inequality, with majorization, which is a set of inequalities. And the answer to this question is no. There is such a thing as a complete set of monotones, only if all the monotones in a complete set decline monotonically. Does R transform into S for free? We've seen an example of a complete set of monotones. The sums, the set of all the sums, in the definition of majorization. Again, we're asking a question about transformations that's more detailed than the question asked in general conventional thermodynamics, which concerns macroscopic systems, thermodynamically large systems, equilibrium states. In conventional thermodynamics, we have to check only one inequality to answer the question. Here, we have to do more mathematical legwork. Let's see another example. This consists of the Rayleigh divergences relative to the uniform distribution of the same size. It'll be useful to see the Rayleigh divergences also because they come up quite a lot in quantum information theory and in the intersection of quantum information theory and thermodynamics in resource theories and out of resource theories. Let's see the definition of the order alpha Rayleigh divergence. Again, let's assume that we are comparing two distributions, R and S, of the same size. Now, we index the elements of each distribution such that Rj and Sj are the probabilities according to the respective distributions of event J. So the probabilities that our random variable X will equal Xj. This ordering is different from our earlier ordering. So earlier, we arranged the R sub j's from greatest to least and the S sub j's from greatest to least. So here's our definition. We denote the Rayleigh divergence by D sub alpha. We're comparing R to S. And it has this definition of many components. We have a fraction. Of course, we have a log because the Rayleigh divergence is a type of entropic quantity. Then within the log, we compare the RJs to the SJs. This is the definition for many of the alphas. Alphas between 0 and 1 non-inclusive, as well as 1 and infinity. The order 1 Rayleigh divergence is a limit, the limit of the expression above, as alpha approaches 1. And also, we have analogous definitions, namely definitions in terms of limits for alpha equal to 0 and infinity. We are now going to start using base E logarithms because we're doing thermodynamics, and the homework will show why using base E is useful in thermodynamics. Let's look at one particular case. Suppose that alpha equals 1. I'd like for you to prove for homework that the order 1 Rayleigh divergence between R and S equals this function. We have an R out front, and in the log, we compare Rj to Sj. That quantity is called the relative entropy, or the Kullback-Leibler divergence. Often called the KL divergence. So the Rayleigh divergence of order 1 is the relative entropy or the Kullback-Leibler divergence. This shows up all over thermodynamics, especially information theoretic thermodynamics. In order to understand the significance of this quantity, we will generalize from the resource theory of non-uniformity by considering a general resource theory of non-equilibrium in which, for simplicity, I'll assume that the Hamiltonian and all of the exchanged quantities, like the particle number operator, whatever is relevant in this physical problem, commute with each other. Since all of those observables commute, they share at least one eigenbasis. Let's denote by ket J the energy E sub J eigenstates of the Hamiltonian and the jth eigenstate of the observable QK for all the observables QK. The particle number of species A, the particle number of species B, the electric charge, whatever quantities are exchanged by the system in the bath. So relative to one of these eigenbases, rho is represented by a matrix that's diagonal. So we can represent the states with a probability distribution R once again. So all of these Renyi divergences of R, now with respect to the equilibrium states, the equilibrium distribution, are monotones under equilibrating operations. I would like for you in homework to prove the following. So I'd like for you to evaluate the order 1 version of this quantity. Let's take the order 1 Renyi divergence between R and this equilibrium state. And let it show that it equals the inverse temperature times a rather large sum. I'll define this quantity shortly. Here's Boltzmann's constant, the temperature, the Shannon entropy of our distribution R, and a sum over the other quantities exchanged. I will define this quantity shortly. Minus negative Boltzmann's constant times the temperature times the log of the partition function of the corresponding equilibrium state. I'm defining this symbol as the average energy. And the analogous Q symbols are themselves defined analogously. They are averages. Now, this equation has a very interesting physical significance. This term in parentheses, I'll write out below, We have the entropy, and we subtract off the terms associated with the other exchanged quantities. This equals a non-equilibrium. Oops, that's okay. A non-equilibrium variance of the free energy relevant to our problem. For example, if the system of interest exchanges heat and particles with the bath, then this quantity comes to equal the grand potential, often denoted by phi, which is defined as E minus Ts minus mu n, as you would expect. Furthermore, this negative kBt log z is the free energy of the equilibrium state. So, since this quantity d1, which equals this difference, is a monotone under free equilibrating operations, according to the results of our resource theory, free equilibrating operations decrease monotonically this sort of non-equilibrium free energy toward the equilibrium free energy. But we learned from the resource theory that also many other quantities decline monotonically, because this is the order 1 Renyi divergence, and there are so many other Renyi divergences associated with other values of the order alpha. Some of those signify the work extractable from a system in one shot if you have as a resource a non-equilibrium system. Another one signifies the work that you would have to expend to prepare such a non-equilibrium state. So thermodynamic resource theories are part of one-shot statistical mechanics, which is a subfield of quantum thermodynamics that I mentioned in an earlier lecture. Here we can think about single trials. This is the end of my set of lectures. Tomorrow we'll start hearing from Matteo. He's going to pick up on resource theories and move forward also with those and with other topics. So it's been a great pleasure lecturing to you guys. Thanks for your interaction, all your participation, and especially for your enthusiasm. Once again, if you feel comfortable, it would be wonderful to see photos of you guys participating, photos or screenshots. You can send them to Gabriel if you don't mind if we post them on social media. It would be a lot of fun to tell a nice story about this course and people's participation in it. So thanks very much.
Great, Nicole, thanks. This was really awesome. And just want to encourage you guys again, please send pictures, not only of screenshots, but also of you participating and watching the courses, and then we can share them on social media. Thank you, Nicole. Thank you very much. And everyone, we'll see you all tomorrow with Matteo's lectures. Oh, and also if you're interested in the reading group, please don't forget to send an email to register. Great. Okay, so see you guys. Bye.